Good afternoon. Thanks for coming to the talk. How are you? Do you like the conference so far? That's weak. That's weak. More energy. Do you like the conference so far? Now we are talking. I know all of you are waiting for lunch, so we'll get through this quickly. Let's get to the important questions first. Sid, what's the lunch menu? It's fine. Okay. All right. So let's begin. I'm Sachin. I lead the video infra team at Facebook. The mission for video infra is to make videos and live successful. So let's look at what we actually work on. We build the infra that powers the entire Facebook video platform. We work on a number of large projects. A few examples here. We try to make our video uploads really fast and reliable. Everybody likes fast, everybody likes reliable, straightforward. We cluster similar videos together so we can show them in related videos and then rank them better. We have built a distributed video encoding platform where we take a large video file, break it up into chunks, process it separately, encode it in parallel, then put it back together. This results in very low latency in transcoding videos. Again, everybody loves fast, not a problem. And we build the infra for Facebook Live. And we will talk a lot about Facebook Live today. Raise your hand if you have not used Facebook Live. No lunch for you guys. Okay. All right, so super easy to use. We'll go through what Live is, and you guys can try it out, maybe even while the talk is going on. That's fine, too. Let's talk scale. 1.23 billion people access Facebook each day. Not in the month, not in the year, every day, 1.23 billion. Let's put that in perspective. The world has about 7 billion people. Many of them don't have access to the internet. So out of the people that have access to internet, a very large number access Facebook each day, and we consider this a huge responsibility. We have to make sure these people get the best experience possible, and we figure out ways to connect, allow them to connect to other people across the world in new and interesting ways. And that is where Live comes in. Facebook Live is a live streaming platform that enables people to broadcast live video streams using just the Facebook mobile app. iOS, Android, we also have desktop apps, and you can go live using a live API if you're a professional or using your own encoder. So this enables people to share everyday moments with their friends and followers. This allows celebrities to reach out to their fans directly. And this also encourages citizen journalism. Ever since we launched Live to the public, we have seen the uptake has been excellent. And we love that. So why is Live different than just uploading a normal video? Well, the key difference is, if you're uploading a video, it could be well-crafted, it could be photoshopped. With Live, there is none of that. You're sharing the moment as it is happening. That authenticity is what differentiates Live from just uploading a normal video. The second thing is, Live is inherently social. There is a lot of interaction. People are commenting, asking questions while the live stream is going on. This way, the commenters and viewers can actually change the direction of the live stream. They can ask you to go do something else while the live stream is going on. And so that social nature makes this powerful as well. And so the interactivity, the authenticity, and sort of sharing the moment as it is happening are the key things that make Live special and different than just normal videos. So let's look at the history. Where did we start, and where are we now? It all started in April 2015 in a hackathon. For those of you that are not familiar, hackathons at Facebook are almost a near-religious event. People from different teams and disciplines get together to build something new, to hack on things, and to be creative. We generally ask people that they should not spend time in hackathon doing something related to their day job. You know, what's the point, right? And so in this hackathon, a group of us got together, and we wanted to build a live streaming backend. So this is a photo. 2 or 3 software engineers, 1 production engineer, TPM, and so on. This hack was called Hack Under the Stars. It was held on the rooftop garden of Facebook's headquarters in Menlo Park, California. We worked on it for a couple of days, 1 or 2 nights. The first live stream that went through our system is very special to us, and you can tell, being the geeks we are, we live streamed the clock. Nothing interesting, just the clock. Now, why the clock? We wanted to measure the end-to-end latency. So you live stream a clock and then view it, and then you can, you can see the difference. Perfect, right? This is what we are. We are geeks. That's what we do. And so remember, people keep talking about the first phone call ever made, and the discussion was, Mr. Watson, please come here, I need you. Well, if live ever becomes that big, remember, 10:03 p.m., end-to-end latency. This is what people are doing on the first live stream ever. So we started with the hackathon. A few months later, we launched it to celebrities. Dwayne Johnson, the Hollywood action hero, was our launch partner. He gave us a really good start. And so from hackathon to launching it to celebrities using the Mentions app, it was 4 months. So we moved really quickly in launching this. Since then, we have had many memorable live streams that I can remember, and I'll share a bunch of them throughout the presentation with you folks. There have also been a few that were a little bit haunting, like the one from the comedian Ricky Gervais, where he went live from his bathtub. I did not need to see that. Come on. Right? OK. So Mentions happened. Then we launched it to users. You'll see about 20 folks here. Again, software engineers, production engineers, designers, and so on. We launched it to users in December 2015. And the 3 screenshots you see are the initial version of live. It's substantially the same even now. So again, hackathon, where we had nothing, we started from 0 to launching it to all users, 8 months. And again, everything we launch on the main app has to work at scale, has to work for those 1.23 billion users who want to use it every single day. So this was a tremendous experience. We loved this. But then that brings us to why live? Like, why did we build this in the first place? 3 big reasons. Engagement. Most things we do relate to whether people are going to like this and whether they would use this, and does this add value to their lives. When we launched live to users, it was clear that we had created something magical and powerful. The engagement was really good, the uptake was good, and so we knew we had something on our hands, and it was worth investing more time and energy into. The second reason was public profiles. We wanted celebrities and public figures to have a way to reach out to their fans directly. So here we have Vin Diesel, another Hollywood action hero. You'll start seeing a pattern. I like explosions, action, that kind of thing. Vin Diesel goes live fairly frequently. That's good. He can reach out to his fans. His live streams are pretty engaging. We have folks like Oprah who go live. Comedians like Kevin Hart use the platform. President Obama, when he was in the office, used to use live. Now I think he's busy surfing in the Caribbean somewhere, so don't see live streams from him anymore. And the third, something that goes to the core of Facebook's mission, is connecting the world. We care a lot about making the world more open and connected, giving people a voice, and sharing different perspectives that are hard to come by in any other medium. So here's an example of some person taking a live stream of what refugees have to go through to get to a better place, to have a better home, to lead a better life. Usually, the perspectives like these, we only get from the lens of a media house. But here you have just a normal person who could go give you that perspective. I think this is very powerful. And this was sort of one of the third reasons why we decided to do live. All right. We have talked about what is live, why we did it, and the history of it. Now let's get into the guts of the infra. We'll talk about 8 different sections, high-level architecture, and then we'll go deeper into each section. We'll talk about the scaling challenges. I will quickly breeze through protocols and codecs, because I know most folks here don't spend their day and night thinking about protocols and video sizes and resolutions, so we'll just breeze through that. Then we'll talk about stream ingestion, stream processing, and playback. We will go through a couple of reliability challenges and some interesting solutions that we came up with. And then we'll quickly touch on new features that are being launched and the lessons that we learned throughout this. And again, we have live streams throughout the presentation. Let's talk high-level architecture. It all starts with the broadcast client. Let's say I want to start a live stream. from here. My phone will create a RTMPS stream. RTMPS stands for Real-Time Messaging Protocol, S is secure. And it will connect to a POP. A POP is a point of presence, which is basically a rack of hosts that Facebook owns. And so it'll connect to a POP. The POP will then forward the connection to a full data center where encoding can happen. So we create different bit rates, different resolutions for a given stream. From there, it goes to different POPs, and so it can go to the playback clients. So if I'm doing a live stream from here, I will connect to a POP close to me. If people in India and the US are viewing, they'll connect to POPs closest to them, and we make sure that full pipe keeps working with super low latency. Latency is actually very important, and I'll go into why soon. Given the network bandwidth required for showing all these live streams to the world, we can't just live with our own CDN. We also depend on third-party CDNs to make this work. All right, let's talk about resource usage. Compute is a primary resource. We require CPU and compute for encoding and decoding streams and for analysis of media. The amount of compute required also depends on number of streams being processed, number of encodings we create, the bit rate, the resolution, etc. We require memory for encoding and decoding streams. Again, depends on the bit rates and the resolutions. More encodings, more memory. Once a live stream is done, we give people the option to store it as a normal video. So they can watch it over and over again. They can share it with their near and dear ones. And so if they choose to pick that option, then we store it in our long-term storage. If they delete it, then it goes away from the storage. And then network. The network required for uploads is not significant, but the network bandwidth required for playing back a given stream is significant. All right, let's look at 3 scaling challenges that we ran into, and then how we solved them. So I've simplified the architecture into 3 broad pieces: the broadcast clients, which is ingest, encoding servers, which is processing of live streams, and then playback clients. Challenge number 1 was how to deal with number of concurrent unique streams. Initially, it looked to be a tricky challenge, but then we realized this has a nice pattern. During the day, we get a spike, and then towards the evening or night, it goes down. Because the pattern is predictable, we can plan resources accordingly. We still have to make some key decisions correctly. We have to pick an ingest protocol that allows us to work across different kinds of networks. It could be cellular networks, Wi-Fi, and so on. It should also be something that can take advantage of Facebook's network infrastructure that is spread through the world. And we have to plan network capacity and server-side encoding capacity for all these streams. The second challenge was the total number of viewers of all streams together. Turns out, this also has a predictable pattern. It is slightly less predictable than the previous one, but there is still a reasonable pattern that we can work around. The things that we had to pick correctly were delivery protocol, which had to take advantage of Facebook's network infra. Once again, the protocols could be different on the ingestion side and the delivery side. Network capacity requirements here are huge, and so we have to deal with that with CDNs and so on. And caching is extremely important. So at this point, we were thinking, everything seems to be going well. Like, everything has a nice little pattern. We can plan resources. Everything works well. And then shit just got real. Right? This is how life works every single time. And I know some people don't like nerdy jokes. So here's a non-nerdy one for you. Right? So this was the third problem that caused us to think a lot about how to solve this. The maximum number of viewers of a single stream. Now, why is this hard? Because it is unpredictable. Unpredictability is the bane of engineering. If you can't predict something, you can't plan for it, it becomes really hard to solve. And so streams could go viral, live streams could go viral without any heads up. Like, it is hard for us to know which stream is going to go viral at what point and why. Because we can't answer that question, solving this problem became kind of hard. And so we had to deal with caching and stream distribution to solve this reasonably. About 10, 15 slides down, we will talk about the architecture on the playback side, and then I'll explain how we dealt with this kind of a problem. So if I was to summarize, how is Facebook Live video different compared to just normal video? These were the 4 challenges. For the Netflixes of the world, you already know your content ahead of time. So you can cache it in different parts of wherever your CDN and POPs are. But for live content, there is no pre-caching. The content is getting created right then. We cannot predict that content ahead of time, so you can't pre-cache. Predicting number of viewers of any stream is not possible. For premium content, like if Netflix is going to launch House of Cards, they know based on last year roughly how many people would see it. We cannot, because random streams become popular, and we cannot predict which stream would go popular when. And so planning for some of these live events and scaling resources based on that is problematic. And then we talked about predicting the concurrent spikes, which are hard to do. So these 4 reasons why Facebook Live video is very different and harder to solve. Let's quickly talk through protocols and codecs. There were many requirements, but these 4 turned out to be the most important. Time to production. We wanted to go from 0, just the hackathon, to production in 4 months and to all users in 8 months. This was a very tight timeline. So time to production was very important. This meant we had to take advantage of everything Facebook had to offer. Network infra, common libraries, everything. You can't build a full system from scratch and scale it to 1 billion users in 8 months. Just not possible. End-to-end latency matters a lot to live streaming. Once you buffer and you batch things up, interactivity is gone. We like the latency to be sub 30 seconds for every stream, ideally in single-digit seconds. With that kind of a goal, you cannot have too many buffers throughout your pipeline, because every time you buffer, you're adding a few seconds of latency, and that adds up very quickly. If you have latency, then it is no longer live. We want to actually be even faster than network TV and so on. So end-to-end latency matters a lot. Because this was going to be part of the Facebook's apps, there was a limit on how much we can add to the application size. The budget given to us was less than 500 KB. So let's look at the protocols that we considered and which one we picked. We looked at WebRTC, which is based off of UDP, which meant it was not compatible with Facebook's network infra, which is tuned for TCP. And so we eliminated that. HTTP upload would have resulted in a horrendous end-to-end latency. Not going to work. We thought about building our own custom protocols, which are optimized for live, built for live. Time to production was a problem. We would have to write our own client libraries, our own server libraries, tune them well, and then launch it to all apps. Unlikely this would have worked in the time frame that we were offered. We looked at some proprietary protocols, which are built for use cases like these. Their application size was a couple of megabytes, beyond our budget of 500 KB. So we couldn't pick that. RTMP satisfied all 4 requirements. RTMP, real-time messaging protocol, is built for video streaming, so it had the right latency characteristics. This is widely used in the industry. So there were client libraries and server libraries that we could reuse, which meant time to production was reasonable. RTMP works over TCP. So this is compatible with Facebook's network infra. And the library size was about 100 kilobytes, much below our budget. So great, this worked out. We picked RTMP, and this has worked really well. The 4 encoding properties that people need to usually care about when doing something like this are aspect ratio. The product requirement was 1:1. That was very straightforward. On the resolution, we started with 720 by 720. As we launched to users all over the world, we realized people may not have enough bandwidth to upload this kind of content continuously. We didn't want people to have jitters or the connection to go away. That spoils the experience of viewers. And so we started supporting a different resolution, 400 by 400. If you don't have enough bandwidth, drop down to a lower bit rate. And audio and video codecs were standard AAC and H.264. These are industry standards, nothing special there. Cool, time for a live stream. This was an interesting live stream of the SpaceX launch. It was awesome to see this on the platform, and a lot of people tuning in, commenting, and so on. There is something beautiful about rocket launches. I don't know what that is, but definitely gets the nerd in me super excited. Like, every time I see a rocket launch, I'm like, great. Maybe it is the explosion, I don't know. The fire and action, maybe that's the interesting part. When this was happening, we were all hoping this doesn't explode, right? This should, and not just the rocket, the live streaming backend as well. Like, we wanted to make sure it all works fine. So this went well, this was cool. I'll show you a different stream later on where we were hoping things explode. Okay, let's look at stream ingest and processing. So I briefly mentioned POPs before. A POP has several racks of hosts which have two responsibilities. One, to terminate incoming connections from clients and then pass these connections over Facebook's network, which is much more reliable. This way, the round trip time is significantly lower compared to people connecting from wherever they are to our DC. And the second is caching. POPs is where we can cache a bunch of these streams for the playback side, not on ingestion. Data centers are much bigger compared to POPs, and they have many more functions. We will look into the details of which functions we end up using for live streaming a couple of slides down. So when somebody wants to do a live stream, they will create a connection to a POP. Before they create the connection, they use out-of-band API to get three things. They get a stream ID, they get security tokens, and they also get a URI. The stream ID is important for consistent hashing. I will talk about that later on. Security tokens are obvious why we need them. And then the URI. The URI gets resolved against Facebook's network infra. We load balance it, and then the client knows which DC or which POP to talk to. So in this case, you see it is connecting to a POP. As soon as the connection is made, the POP will forward the connection to a DC. This is where the stream ID comes in. We need to map a given stream to a particular data center. Which data center it picks is not super relevant. The important part is it picks something such that things are balanced well, and then it keeps going to that DC for that stream, so we don't have jitter and lag. This is a flattened topology of what we just saw. Broadcast client connects to a POP, connects to a DC. Now let's get into the details of each one of these. There's going to be some cool animation here, by the way. You can see I get excited about these things. All right, so let's go inside a POP. As I said, it has two types of things. Proxygen hosts, which are responsible for terminating the incoming connections, and the big cache hosts responsible for caching. On the ingestion side, caching is not relevant, and so we can ignore that for now. So the broadcast client creates a connection with a random Proxygen host in the POP closest to it. The Proxygen host has scriptable logic, which we can write and determine what to do with a given stream or a given connection. In case of live streams, the logic is send this live stream to an appropriate DC data center based on load balancing. And so that is what it does. Now let's look inside the data center and see what happens there. That is where the real processing happens on the ingestion side. Animation. So it has three types of hosts. The Proxygen hosts and the big cache hosts, they have the same function as the two types in the POP. And then there are the encoding hosts, which are the owners of a given stream. And we do a bunch of processing on the encoding host. We will ignore the big cache host for now. Caching is not relevant on the ingestion side. The broadcast client creates a connection. The POP forwards a connection to a random Proxygen host in that data center. The Proxygen host does consistent hashing on the stream ID and sends it to an appropriate encoding host within the DC. When we started, we were actually doing this mapping based on the source IP. And then we realized with NAT and all that fanciness, we would end up mapping a lot of machines to a lot of streams to the same machine, and this was not cool. So we moved to stream ID, and that worked out much better. This mapping is important for a variety of reasons. If a client loses its connection because they move from cell to Wi-Fi or the other way around, we don't want the stream to have jitters. And so in this case, the connection goes away. The broadcast client creates a new connection with the new network, but uses the same stream ID, and so it gets mapped to the same host. So viewers of the stream would not even realize that all this happened behind the covers, which is exactly how it should be. This logic also allows us to deal with planned and unplanned outages. At our scale, planned outages and unplanned outages happen every day. There is just no way around it. And so in this case, let's say you lose the encoding host. So the connection is gone, the end-to-end connection breaks away. The broadcast client will create the connection again. It will go to the Proxygen host. The Proxygen host will realize that the encoding host, which was supposed to be responsible for this, is down, and it can no longer talk to it. It uses consistent hashing to find the next host that should be able to take care of the stream and start sending the data to that host. Depending on how long it took for us to realize that the host is down, there may be a small jitter, but in most cases, you wouldn't even notice that all this is happening behind the covers, which is great. Works out well for everybody. Works out well for us. Don't get called for on-call issues. Works out for users. They get a smooth stream. Awesome. So that's what happens at the DC. This is sort of the ingestion and the processing side of things. Let's look at the encoding hosts and what they do. Encoding hosts do 5 things. The first one is authenticate a stream. So they make sure a stream is proper and formatted correctly and so on. They associate themselves with that stream. So now they are the owner, they are the source of truth for this stream. This is important because when we talk about playback, the playback clients and the POPs need to know which host to fetch data from. And so encoding hosts are the ones that tie the ingestion side and the playback side together. The encoding hosts create several encodings. So whatever quality we get, we create multiple encodings, some lower quality with lower bit rate, so we can show the live stream without jitters to people who don't have enough connectivity. They create the playback output, which is dash, and we'll talk about dash in the next section. And they store media. So we talked about how live streams become normal videos. Those get stored. The encoding hosts are responsible for converting them into videos and then putting them out in our long-term storage. Time for a live stream. This one, we wanted things to explode. And here's why. This was a live stream. It will show up, by the way. It's not an error. I'll click a button and it'll show up. 2 employees of BuzzFeed decided to find the breaking point of a watermelon by putting rubber bands over it. They went on for 45 minutes and put 690 rubber bands, and then it exploded. Here it was. You'll see the explosion in action. See? Then they proceed to eat it, which is fine. So we have different kinds of live streams. There are rocket launches, and then there are watermelons exploding. Who's to say one is more important than the other, right? They're all good engagement, work out well. All right, let's talk about the playback side. MPEG Dash. So what is Dash? Dash is a streaming protocol over HTTP. Super simple, actually. It consists of 2 types of files, a manifest file and media files. Manifest file is a table of contents. It just points to media files. So server creates 1-second segments. So as a live stream is being created, for each second, we end up creating a segment and then update the manifest to point to this new segment. So as the stream is going on, the manifest can keep increasing, and so we keep a rolling time window. If a stream goes on for several hours, it is not super useful to send the entire manifest to all clients the entire time, because this is supposed to be live. Client refreshes the manifest periodically using standard HTTP GET. When it sees that there are new entries in the manifest file, it will go and fetch the corresponding media files, again, via HTTP GET. So it's a straightforward protocol. It also allows different bit rates for the same stream and then syncing them appropriately, which is, again, important when your bandwidth is varying, which happens a lot. So more animations, now from the playback side. So let's say this playback client is somewhere in India, and we are going to use the blue square, which is at the encoding host, as the source of truth, or the file being requested. It is sort of the precious. So the playback client will connect to its closest POP and say, give me the manifest file for this stream. Let's assume this is the first time anybody has requested the manifest file for this stream. So the only place where this is available is on the encoding host. The proxygen host checks with its local big cache host to see if something is available. The big cache host says, nope, there's nothing there. The proxygen host then makes a call to the data center that is supposed to be responsible for this stream and connects to a random proxygen host there. There, it checks locally again with a big cache host. Again, figures out there's nothing on the big cache host either, because again, this is the first time somebody is fetching this manifest. And so it knows which encoding host to go to based on the consistently hashed stream ID, goes to the encoding host, gets back the manifest. It then populates the cache, sends it back to the proxygen in the POP, which in turn again populates its own cache, and then sends it out. Now, all of this may seem like a lot of work, like why are we populating all these caches? This becomes relevant when some other playback client comes in and connects to the same POP. Here, the proxygen host will talk to its local big cache host, finds the file, sends it back. Did not even hit the data center. So remember, we talked about a stream with a large number of viewers that we couldn't predict which stream would be. Using this two-layer caching architecture, we can solve this problem reasonably. Because the first time somebody connects to a POP, we fetch it from the DC. Everybody else who connects to the same POP no longer needs to go to the DC. They get everything they need right from the POP. And so you can scale out by POPs and DCs separately and have separate caching architecture in both of those places. Now let's see what happens if, let's say somebody in the US wants to see this live stream. And so they're going to connect to a different POP. Now this POP doesn't have the manifest file yet. So it goes through the same motions, checks with the big cache host, doesn't have it, goes to the DC, checks with the big cache host there, finds it, fantastic, returns it, caches it locally, and out. So roughly, you can see that the number of requests that the DC would get is equal to the number of POPs. Because once you have it in the POP, you're done. That POP will take care of the manifest file itself. Now, we also need to update the manifest file periodically, and there are two ways to do this. One is have a small time to live, TTL, which is a common jargon used with caches, where this will fall out of cache in, say, 3 seconds. And the next person coming in will go to the DC and fetch the updated manifest file. Or we can use HTTP push and push this out to the respective POPs as required. The second one is better than the first one, but maybe slightly more complicated. I think Todd gave a good talk on async yesterday. I think the push mechanism sort of ties into that kind of thing. All right, let's talk about reliability challenges. Quick reminder, this was the original architecture we talked about. There is a big problem that we had to solve, and it was a network problem on the ingestion side. If we can't get the stream ingested, nobody can see that stream. And so ingestion problems end up causing a bad user experience across the board. And so we had to solve it when the network is bad. Now, if the network is just gone, if there is no connectivity, there is nothing we can do. The stream is just gone. People will go find something else to watch. But if the connectivity is lower, the bandwidth has gotten lower than what it was before, then we can do interesting things. We use something called adaptive bitrate. Adaptive bitrate is typically used on playback side, where when you're watching videos, you will see if your bandwidth goes down, you start seeing lower quality videos. We also apply the same concept on the ingestion side, where if your connectivity goes down or your bandwidth reduces, then we can send in a lower quality stream. Now, this is not something that we like to do, because who likes lower quality videos? But the choices are either the stream is broken or you see a lower quality stream. And so we have to make a compromise there. When you think of connectivity problems, people typically think of areas like these, where you don't know what's going on. You'll be surprised to hear that there are connectivity problems in very interesting areas of the world, like the White House. Terrible Wi-Fi. We could not believe it. They tried to go live a couple of times, didn't work, and we were like, how? We never thought that Wi-Fi would be a problem. But well, they do. Now we know. So dealing with network problems, 3 different solutions. We talked about the adaptive upload bitrate. We can handle temporary connectivity loss by buffering on the client. This is one of those times where we are OK with buffering to avoid cutting the stream off. In the worst case, where there is just not enough bandwidth to send a picture stream over, we can do an audio-only broadcast, where what you're seeing is more important than what people are seeing. Audio-only broadcasts work fine. Cool, let's talk about the second problem, thundering herd. Everybody loves thundering herds. There's more explosions here. So let's say the particular stream is popular, and so a bunch of playback clients are asking for that stream. Again, we have the blue dot only in the DC at this point. The Proxygen hosts all make connections with that one big cache host that is supposed to be responsible for the stream. We don't allow all the streams to go to the DC right away. We block them using a cache blocking timeout. This timeout is important because there is no point in sending 50 requests over to the DC right away. We can send one, and the rest of them can wait for the response from this. This works well if the response arrives in time. Sometimes the response doesn't show up in time, and then the timeout expires. This unleashes a thundering herd. Everybody who was waiting for the cache to be filled now goes to the DC. Guess what is going to happen? Guess. Fire. So this is bad. Now, the way around this is tuning of cache blocking timeouts. If the cache blocking timeout is too high, then losing even a single request will result in stuttering of the stream or jitter. If it is too low, then we get frequent thundering herds. So tuning this is a little bit of black magic, a little bit of art, a little bit of science, but we have sort of gotten to a reasonable place over the years. All right, let's talk about new features. This is exciting. So broadcasting live is one experience, but wouldn't it be cool to add somebody else, to add a viewer into the stream to interact with you? So imagine Vin Diesel goes live, and I get to join that broadcast stream and ask him a question directly. That would be fantastic. And so this is what this feature is. It is being rolled out now, where a broadcaster can add a viewer and then interact with them in real time. The infra challenge here is, now these two people are talking in real time. You can't have seconds of delay. It has to be milliseconds for them to have a reasonable conversation while everybody else is watching their conversation. So that was an interesting challenge that we had to look at. Video tab is out to some people at this point, where the key challenge here is we have to pre-buffer several different video streams and push them out to the clients. Video tab allows people to watch top live streams, recommended live streams, related videos, or a lot of content from their friends and followers and so on. And so buffering all of that and pushing it out was an interesting problem to solve. We also allow casting of live streams to different screens, like your TV. Facebook recently launched a Facebook video app for TV, for Apple TV, for Samsung TV, and Amazon Fire TV. And so now you can watch interesting content there. The holy grail of immersion is 360 Live. This is where you can transport a person into a completely different experience as it is happening live. Super exciting. The hard problem, though, is As if just normal live 720 by 720 was not hard enough, now you have to do a 360 view of that entire thing. So tuning our entire stack for super high bandwidth streams like these was a challenge. Now all the people who said they haven't tried live yet aren't you repenting that? You can try it now and you'll see how cool it is. Okay, let's look at some lessons learned. Large services can grow from small beginnings. Sometimes it is not possible to predict that something will become so successful or big, but you have to start somewhere. It is better to actually write some code than keep discussing forever on what the ideal architecture should be. You have to adapt your service to the network environment that you have to operate in. This means bad connectivity, bad networks, people moving from Wi-Fi to cell, and so on. Dealing with all of those aspects is important to make a product successful. Reliability and scalability are built into the design. You cannot add these later. This usually does require more time than people like to budget for, but I think this is very important. Hotspots and thundering herds are my best friends at this point. They happen in every component, and I have to deal with them anyway. All of you have to as well. The design has to accommodate for planned and unplanned outages. If you don't, things will keep going down, on-call will be hell, you will not be able to get any work done. And so dealing with this is very important. You have to make compromises to ship large projects. We have to compromise a lot in terms of what protocol we use, what quality we support, and so on. But these were important compromises to be able to launch and have a reasonable service. It doesn't feel good to make compromises, but it is the right thing to do. And keep the architecture flexible for future releases. Doing things like a broadcaster adding a viewer can be pretty tricky if the architecture is not right. And so flexibility is very important when you're working with product teams that are moving way faster than an infrastructure team can move. So flexibility becomes key. Cool, these are some of the sources. A bunch of people helped out with the slides. The 2 images for shit got real and so on. All right, thank you. Time for questions.
Okay, so we have a few minutes before lunch for questions. One thing that Sachin didn't have in his talk, which I asked during a preview, was how they deal with porn.
With what?
Porn.
Porn.
Do you want to answer that question here?
I like action movies, not porn. So porn has to be dealt with carefully. There are a bunch of things. If people report porn, then we actually have humans looking at that to take it down. There are also some automated flows to take down porn. So it is a combination of those two. But it's a hard problem.
All right, no pun intended.
Oh my God, yes.
Anybody else? Any questions? We'll probably cut it out in we'll take a few questions since it's lunch.
I think there is one there. Sid.
Hi, first, thank you. It was a very entertaining talk. My question is, as far as I understand, most viewers of a live stream are more likely to connect to a POP rather than the data center, right? Because they're most likely to be collocated to the live stream presenter. So in that case, it seems that latency is not that big of a deal because you would rarely connect to a data center. So on your average case, latency shouldn't be that much of a problem. Is that correct?
Actually, latency is still a problem because, as I said, let's say I'm broadcasting from here. People could be in different parts of the world. Not everything, so even engineers like to believe that everything travels at the speed of light, but when you send it over 15 different networks, different peering arrangements, and so on, a lot of latency gets added. Two, we have to encode these streams to account for the bandwidth available on the viewer side. That encoding requires a buffer for it to do a reasonable job and create a good enough quality with a lower bit rate. And so that adds latency. The different protocols, I talked about Dash. There are other protocols like HLS and so on. Each one of those have their own requirements on how much buffer they need before they will start playing. And so there are several factors that go into that, and so latency actually is a problem, and we have to tune it really well to have a good experience.
Fair point. Thank you.
Hi. Thanks for the talk, first of all. A couple of questions on the back end of the data center. Do you use containers on the back end, and how do you deal with storage? How do you provision it? How do you keep up with it?
So we use Linux containers, and on storage, we have our own system that we have talked about publicly called Haystack or Everstore, and we use that system for, somebody's waving. We have a system called Everstore, which stores all the photos and videos that we have. So it's a dedicated system for these kinds of use cases.
I wanted to ask you, did you guys consider using the Quick protocol instead of TCP for uploads or streaming?
So we are considering Quick now. We didn't consider it then because our network infra is tuned for TCP. And so since time to production was a key requirement, we went with whatever helped us get into production sooner. But now that we have sort of more headroom, if you will, we are going to try a reliable UDP and a bunch of those things.
Hi. You've been talking about seconds of latency in your streaming over here.
Okay.
No, that's not me.
You've been talking about seconds of latency in your streaming, but towards the end you talked about a new feature where you're having person-to-person conversations, where you need to be down to milliseconds. How are you tackling that?
So to tackle some of those things, we have to look at different protocols. RTMP won't do because it can't do 200 milliseconds or so. So we look at WebRTC. We already have WebRTC support for real-time calling on Messenger. So Messenger has video calling and voice calling, and so we can use a similar stack for people talking in real time.
Okay, hi. How do you differentiate between the amount of people who are watching live streams? So because there are live streams which are watched by, I don't know, thousands of people, and some are watched by like 2 or 3. So you still put those meta files into the caches. Those magic boxes, big caches, are like components that manage all those things?
Yes, so it depends on, if you have one viewer, then a cache is useless.
Yeah,
but
exactly.
we can't predict that you will have one viewer only.
So that was just a simplification of like the putting everything into the big cache.
Yes.
Okay.
So if you have 2 users watching us, hopefully they're in the same POP. So caching it in that POP makes sense. If you have one, then yes, the cache is pretty useless.
Okay, thanks.
You released live first for celebrities and then for the rest of the public. Was that done for performance reasons or for marketing reasons?
Sorry, I didn't hear the first part.
You released live first for celebrities
Yes.
and then for the rest of the public. Was that done for performance reasons or for marketing reasons?
So we wanted to figure out if this is something that we should invest in more. That is one. And 2, it is good to try things out and see how they work to validate our assumptions in production. If we launch it to all users, then it becomes a much larger problem to deal with. Mistakes get amplified. With celebrities, it is a small set, but they still end up testing the limits of our infra, because celebrity streams will typically have a large number of viewers. And so we get all the testing we need in production instead of just doing our own shadow testing and so on.
Yeah, hi. So when you guys started, so what was the team size? And when the idea becomes the reality, how the team grown up?
So initially, as I showed you the first picture, it was basically a very small set of people that built the infrastructure. And it was just those people who launched it out on the Mentions app. Once we figured out that this is working well, and we need to invest a bit more to launch it for all users, we added a few more people. I'm not entirely sure we have talked about the team sizes before, but teams at Facebook are typically very small. In the morning, I think we saw how teams of sizes more than 20 fail miserably. We have already taken that to heart. We typically have very small teams, a close set of people who work together and deliver things. If we need more people with different skill sets, we form virtual teams. And so there'll be a couple of people from product, a couple of designers, a few infra engineers. They sit together for a few months and then hammer out the required code.
Have you considered using a third-party media server, at least during the prototyping phase, before you develop your own, or?
So most things in the industry don't work at Facebook scale. And so it is OK for a prototype, but we know we have to throw that out anyway before we put it into production. And so we typically build our own, or if we end up using something that is open source or so on, like we use MySQL a lot. We make a lot of changes so it can scale and operate at our level.
Okay, out of curiosity, which, for your prototype, did you use one? Can you tell which one you used?
We didn't use a media server. We built our own.
Okay, thank you.
I'm curious, you say you encode things to multiple different formats for different devices and things. Do you do that on the fly in terms of creating a new stream per set that needs it, or do you do them? Do you do all the different formats ahead of time, just in case you need them? In which case, surely that wastes a lot of CPU.
It is a mix of things. We can make some assumptions about what formats we are going to need, but I think that is one area where we need to invest a lot more to save CPU. You're right. Efficiency is starting to become a problem, and so we'll look into that.
Okay, great questions, everybody. I think it's time for lunch. If you have further questions, please come up to the stage and ask them. Thank you very much.
Thank you.